right, it looks scary, which scary things are often very cool. The idea is this. If you can find the area under a curve, so we're going to look first at this shape on the left. This looks like maybe a 1 over x graph, something like that. If you could find the area from here to here under that curve, well, we could do that using a definite integral. Then, if you took that area and you rotate it 360 degrees around, can you see that it would fill this shape? And then you would have, and since we're filling the shape completely, that becomes a volume. So now how do we do that with calculus? First of all, the idea is if you were to take any little piece of the area, so like a small tiny piece of the area like this, so small that it just becomes a single line, and you rotate that line all the way around, what shape do you make? Right? It would be a circle. It doesn't look like a circle on the board because it's three-dimensional right now, but if you turned this and looked at it straight, you would have a circle there. And if you did it at another point right here, well, and you rotated that radius around 360 degrees, you'd make a circle there. So it's kind of the same idea as figuring out the volume of a cylinder. Now, a volume of a cylinder, I don't know if you remember the formula, the volume is pi r squared times the height. Because if you start on the bottom of a cylinder, it's a circle. And if you kept cutting out circles and stacking them on top of each other, you would eventually build a cylinder. And since if you added up all those circles that were stacked on top of each other, you would get the volume. Well, how do we do all of those circles? Well, we have one circle, pi r squared, and then we multiply it by its height. So now, how do we do it if our circles get bigger and smaller as we go along? The radius is changing. Well, that shows up here in our integration. In our integration, as we go and find the area under the curve, we're finding all of those little radiuses as they change as they go. So now, if we figure out that the area is going to just be a circle, and our radius is actually our value of our function at that point, if we integrate pi r squared, so if we integrate from whatever value to whatever value, we all of a sudden get a volume of that shape. And we can figure out some very, very cool volumes as a result. And then if you extend it even further, and you say, in the second example, here's my two functions. And the area between those two functions is blue. If I first did f of x and rotated all the way around, I would get a bell that would be solid. Wouldn't be a very useful bell because nothing would ring inside of it. Then if I took my second function, g of x, and rotated it around 360 degrees, I'd get a little bell that would be solid and wouldn't ring very well. But if I subtracted the little bell out of the big bell, I would get a volume for this shape. And the yellow here shows that it's hollow in the middle. And that blue part would get rotated 360 degrees around. And now you can figure out volumes of crazy looking objects, as long as they're symmetrical, because you're rotating them around 360 degrees. But a bell is a very good example of that. All right. So here we go. Our volume is just, and you can have the pi inside or outside. In our formula booklet, the pi is inside, and instead of f of x, they have y. There's so much fun stuff we can do. We can like find the volume of a cone using this. Because all a cone is a straight line that's been wrapped around. And it's an actually very easy integral. So you can make up formulas doing this. But wait, maybe we'll get to that. Maybe I'll get off topic and like find some formulas for you. But right now, let's just look at a couple of examples. We're going to take x cubed. We're going to look at it from 1 to 2, and we're going to rotate it about the x-axis. That's what it kind of looks like. Should I draw that again slower? Okay. Start with our axes. Here's x cubed. If we went from 1, which we'd have 1 comma 1, to 2, we would have that as an idea. Now I'm going to use the line from 2 to 8. That line has a length of 8. So if I rotated that line 360 degrees around, it would make a circle with a radius of 8. So I'm going to try and draw that. Can you imagine that as a circle with a radius of 8? And then over here, with a radius of 1, I'm going to draw another circle. And so now I have to imagine joining those together and shading it in. I don't know, I think the other picture before might have even been better. Yeah, that looks pretty awful. But in the end, we should have something, if we expanded it out a little bit further, we should have something that looks like that, with this part here being the curve x cubed, and then it rotated around. So you can have, like, you know, for the artistic people in here, you can add fancy shading to sort of give that three-dimensional look to it. Nice. Beautiful. So these are the horns that people play at sports games. And so as we set it up, our volume will be the integral from 1 to 2. Pi can come out in front, and it's our original function squared. Just like it's pi r squared. So our original function becomes the radius. Then we can square our original function. The integral itself isn't hard to do. The numbers aren't the nicest, but they're not too bad. And we get an answer for that volume. Now you think back to grade 11 if you were trying to do this. I don't know how I would even, like the area one I could at least, oh wow, good morning. Sure. Here's our second example. Here is the picture. This one's a little bit, I'm not going to redraw this one because this one's really nice looking. So we got our square root of x. That's right here.
Now you could get the volume of a ham.
Yes, this is the ham function. In fact, we should probably color it in to make it look pretty with crayon, red crayon, because it's a ham bone. I know you guys are getting hungry.
It would be nice if they really brought ham. Would you like it? Would you like a whole ham?
So now we just have to find the integral. And the nice thing about the square root of x minus 1 is when you square it, the square root goes away. And it's a super easy integral to figure out. So there's our integral, and we won't worry too much about the numbers, but plugging things in. Can I scroll down a little bit further? How many pies can you fit inside of a ham? 8 of them. Oh, boo. All right, so now we're going to look at what happens when you go from 0 to pi over 4. You're looking at the area between sine x and cos x, and you're going to rotate that. So I'm going to try and draw this out. I'm going to draw it out a little bit bigger. Here is cos. Here is sine. If you rotated this 360 degrees, can you see it would kind of make like a dog dish? But on its side, like it would make a dish with a tiny little hole, so that if you poured water into it, it would drip out. But maybe the hole's so small that it wouldn't drip out. So this part here would be circular. And yeah, again, my artistic abilities with my left hand are pretty bad. Because you're going to imagine this little part going all the way around. So this part will all be solid here. But in here on the inside, that part's going to be all hollow. Yeah, that's a little bit better. It's thick at the bottom, and it has a tiny little hole in the bottom thing because it got punctured right through. So the idea is this: if you can find the volume of one of them and subtract the volume of the other one, then we can find the area. Notice that we can't just do cos minus sine and square the whole thing. We have to do the whole volume of cos first, the whole volume of sine second, and subtract those volumes. So it comes out to be cos squared minus sine squared. And then we're trying to calculate between 0 and pi over 4. Two different ways you can do this integral. You could have integrated both cos squared and sine squared, but that's going to be hard, right? Because then you've got integration by substitution because it's chain rule, but you don't have all of your information for the chain rule there. So both of those would be hard. But if you recognize cos squared minus sine squared as an identity, and you can rewrite it as cos 2x, now the integral becomes doable. Because it does have a chain rule, but you'd have to divide by 2. And then now we're just getting into the calculation parts. And you get pi over 2 as the volume.